Let's begin with the big idea behind the Fourier transform. As the width of the domain for a Fourier series grows larger and larger, toward infinity, the discrete set of frequencies we normally use gets closer and closer together. In the limit, this discrete set of frequencies blends into a continuous spectrum, and this idea leads us directly to the Fourier transform. The Fourier transform of a function, f of t, is defined in words as follows. Take the function f of t, multiply it by e to the power of negative I omega t, and integrate this product over all time. In symbols, this is written as the Fourier transform of f of t equals integral from negative infinity to infinity of f of t times e to the power of negative I omega t dt. Now let us find the Fourier transform of a specific function called the rectangular pulse. The rectangular pulse function f of t is defined piecewise. It equals 1 for t between negative a, and it equals 0 everywhere else. Because f of t is 0 outside the interval from negative a to a, the integral over all time collapses down to just that interval. So the Fourier transform becomes integral from negative a to a of e to the power of negative I omega t dt. To carry out this integral, we first find the antiderivative of e to the power of negative I omega t. The antiderivative is e to the power of negative I omega t divided by negative I omega. Now we evaluate this antiderivative at the upper limit, a, and subtract its value at the lower limit, negative a. This gives 1 divided by negative I omega times the quantity e to the power of negative I omega a minus e to the power of I omega a. Using the identity that connects e to the power of I theta and e to the power of negative I theta to the sine function, the quantity in brackets simplifies to negative 2 I times the sine of a omega. So we get 1 divided by negative I omega times negative 2i sine of a omega. The negative signs and the i's cancel neatly, leaving a real valued result. Carrying out this integral gives the transform 2 times the sine of omega divided by omega. Now let us check this result carefully, especially at the special value, omega equals 0. We must check this case separately, because dividing by omega is not valid when omega itself equals 0. Let us go back to the original integral and set omega equal to 0 directly. When omega equals 0, e to the power of negative I omega t becomes simply 1, so the integral becomes integral from negative a to a of 1 dt. This integral evaluates directly to 2a. Now compare this to the limit of our general formula as omega approaches 0. As omega gets very small, the sine a of omega behaves like omega itself, so 2 times the sine a of omega divided by omega approaches 2 times omega divided by omega, which simplifies to 2a. This matches exactly the direct calculation we found at omega equals 0, confirming that our formula for the Fourier transform of the rectangular pulse is correct.